All right, so to start this off, we need to start with some intuition about what the number e is and what it represents. And I'm actually going to start with a non-calculus interpretation of this, and for that I'm going to defer to the world of finance because that's where this constant it was originally discovered by Jacob Bernoulli when dealing with problems of compound interest. So here I have a formula for compound interest. This is A represents the final amount of money, P represents the initial investment, or the principal amount, R represents the annual rate of interest, and T represents the amount of years. You see annual rate of interest and the amount of years. So these two numbers are related. This is the percentage of interest that you're dealing with over the time period, and this is the number of time periods that have passed, but in this case it's just annual and number of years. And so let's say that we're dealing with a very generous bank that has offered us a 100% annual rate of interest. And so if I put $2 into this bank over the course of 1 year, I should expect to have $4 as my final amount. And I'm actually only going to deal with $1 investments, because if you think about it, if I put in $5 into my bank account, that's going to turn into $10, but that's the same as putting in 5 individual $1 bills, and then each one of those growing on their own, and then adding those back together. So if I'm just going to analyze what happens to $1, I can extrapolate that out further and see what happens to larger and larger investments. So I'm going to make P equal to 1. And let's just see what happens after 1 year using these substitutions. So I would have 1 plus 1 to the power of 1. And as you might expect, with a 100% annual rate of return on a $1 investment, I'm going to be left with $2 in the bank by the end of that year. But banks don't typically calculate interest in this way. Usually they calculate interest continuously and then just pay that interest amount out to you, usually once a month. And so how would you calculate interest continuously? Well, if we wanted to calculate interest once every month, then we would have to do this to the power of 12. But if you plug this in, you're going to get 2 to the power of 12, which is going to be some ridiculously large amount. And so clearly we have made an error here. And the error is that we're using our annual rate of interest, and we're applying it over shorter and shorter time periods. So effectively what we are doing here is doubling our amount every single month. That's not what we want to do. Actually, what we need to do is take our annual rate of interest, 1, and divide it by the amount of time periods in which we are going to apply that rate of interest, which in this case is going to be once every month, so we're going to do it 12 times. And divide that annual rate of interest by 12. Then we're going to apply that over 12 different time periods, and we're going to see what we get. And if you plug this into your calculator, you will get, I'll type it in right now, looks like 2.61305, etc. And so what if we wanted to calculate this continuously? Well, now we have calculators, we have machines, so let's just do this once every second. And so in order to do that, we're going to do 1 plus 1 over, well, how many seconds are in a year? You have 365 days times 24 hours in a day times 60 minutes an hour times 60 seconds, and then we would have to raise this to that power, 365 by 24, 60 by 60. And what would this get? Now, if you actually plug this into your calculator, what you'll find is that this number is going to approach something like this, 2.7182 blah, 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 blah. And you might be surprised by this. When we went from going to compounding interest once every year and just using our annual rate of interest, we doubled our amount. And then when we did it once every month, we got a little bit more than double. We got 2.61305 times our original amount. But then when we went from doing it 12 times per year to once every single second of the year, which is an extraordinarily more frequent amount of time to be doing this, we only gained about 10 cents. And so what's going on here is that if you take the limit of this expression as n approaches infinity of 1 plus 1 over n to the power of n, this is going to approach this constant, 2.7182, etc. And the reason for this is because this constant is a fundamental constant of nature that deals with populations which grow in proportion to the size of the population itself. So this is going to happen when you're dealing with money, where the rate at which that amount of money is growing is dependent on the amount of money that's there in the first place. It also happens when dealing with population sizes of animals, of different species, because the larger that population grows, the faster that it's going to grow because there's more members of the population with which to reproduce. These things, real world variables, are affected by different compounding variables. So for example, population sizes can't grow without bounds because there's limited resources with which to support them. But in the world of mathematics, when we're dealing with this type of growth, and we can say that it grows without bounds, we say that these things grow exponentially. And this constant, known as E, is a fundamental constant of nature that is a consequence of what happens mathematically when you have these populations growing at a rate that depends on how that population itself grows. So this is a non-calculus interpretation of what that number E actually represents. So, going back to this example, after 1 year, if I put $1 into the bank and I compound interest continuously, as banks often do, I'm going to be left with $2.7182 in my bank account with a 100% annual rate of interest. If I wanted to do this for different annual percentage rates, which banks obviously do, they're not paying you 100% interest, then I would have to put in a different number here instead of 1 for my rate of annual interest. And so you could have something like limit as n approaches infinity of 1 plus r over n to the power of n. This is going to represent the amount of money that you would have in the bank after 1 year at an annual rate of interest of r compounded continuously. But what about after 2 years? You can't just multiply this number by 2 because that's not what happens when things grow continuously. Really, what you need to do is make this amount the principal amount for the next year and then multiply by this same expression, the limit as n approaches infinity of 1 plus r over n to the power of n. This is just applying this formula, basically, but compounding it continuously and then subbing in the result of this after 1 year for our value of p and then plugging it back into the formula to see what happens after 2 years. And if you do that, you're effectively just squaring it. You're multiplying this value by itself. And so really, it's not even necessary to write this out. We could just multiply this to the power of 2, and that's what would happen after 2 years. Similarly, if we were to put this as our principal amount, after 3 years, we would multiply this value by itself again, and we would raise this to the power of 3. And so essentially what we're doing here is we're raising this to the power of t, where t represents the amount of years that have passed. And in finance, they typically reduce this down to say that this is equal to your principal amount times e to the power of rt. And the reason that that works is because this expression inside here, the limit as n approaches infinity of 1 plus r over n to the power of n, this is equal to e to the power of r. And when you raise this to the power of t, it's the same as taking the product of those two exponents for the base e. And so that's where this formula for continuous compound interest comes from. And then we can start to get a sense of why we might want to analyze the function e to the power of x. E to the power of x. So we have a little bit of intuition now, based on our example of compound interest, about how e to the x, the exponential function, is going to be useful in dealing with situations where we have populations or things like money which grow in relation to their own size. And you can imagine that in nature that's something that's going to come out pretty frequently. And so this is a useful function to be able to understand mathematically. But now we're entering into the world of mathematics, so we can abandon these real world examples for now, and we can deal with this in the purely theoretical, purely abstract realm, and that's going to make it a lot more easy to work with. And furthermore, I'd actually argue that this is going to make the function a lot easier to understand. And the reason is because in calculus we have tools such as the derivative. And what does the derivative represent? Well, our derivative is going to represent the instantaneous rate of this function, rate of change of this function at any given point. And intuitively, based on our example of compound interest, we might expect that that derivative is going to have something to do with the size of the function at that point, namely the function at that point. We might have to, we would assume that it would be somehow related to that. And so what I want to do in order to understand this function a little bit better is I want to try to take the derivative of e to the x. Take the derivative of e to the x. So let's just take a shot at this derivative using the formal definition, and let's see what happens. We're taking the limit as h approaches 0 of f of x plus h, which in this case is e to the power of x plus h minus e to the x, all of that over h. And what I'm immediately noticing is that this first term, e to the power of x plus h, we can sort of expand that out, getting e to the power of x multiplied by e to the power of h. So we get e to the x times e to the h minus e to the x, all of that divided by h. Now what I'm noticing is we can factor out an e to the x, And I'm also noticing that this limit here is dealing with the variable h, and so e to the x doesn't have an h in it. That's not dependent on, or this limit is not going to have any effect on the variable e to the x, or the function e to the x. So we can actually pull that out of the limit, not just out of the numerator here. And so we can say that this is equal to e to the power of x multiplied by the limit as h approaches 0 of e to the power of h minus 1 divided by h. And so our intuition seems to have led us in the right direction. It does appear that the derivative of this function, the rate of change of this function, is dependent on e to the x. But it's being multiplied by this limit over here, the limit as h approaches 0 of e to the power of h minus 1 divided by h. And so although it is proportional to the function itself, we still have this expression here, this limit as h approaches 0 of e to the power of h minus 1 divided by h, that we have to deal with in order to get a precise answer for what the derivative of e to the power of x is. And this is actually very challenging. And if you look around on YouTube for a proof of the derivative of e to the x, you'll actually find a surprising lack of resources. For instance, if you look at the Math Sorcerer's video on this topic, his method of proving the derivative of e to the power of x was to involve the natural logarithm. And using the derivative of the natural logarithm, he was able to prove the derivative of e to the power of x. And if you don't know what the derivative of the natural logarithm is, or if you don't even know what the natural logarithm is, it doesn't matter. The point is that the derivative of the natural logarithm is by definition dependent on the derivative of this function that we're dealing with here, e to the x. So using a function that is dependent on the derivative of this function in order to prove the derivative of this function is completely a circular argument. And that is not a rigorous, good proof. Khan Academy has, in my opinion, a better video on the topic, wherein they use a substitution here in this numerator in order to try to solve this limit. But in the end, what they wind up with is an indeterminate limit, wherein, for example, if you were just to directly substitute h is equal to 0 into this equation, you're going to get e to the power of 0, which is equal to 1, minus 1, which is 0, divided by 0. And that's exactly what Khan Academy winds up with, and they essentially just hand-wavingly say, oh, this is equal to 1, which, once again, is, you don't know what that is. You can't say that 0 divided by 0, the limit if that is equal to 1. I think the reason that there is a lot of hand-waving when it comes to this limit is because it's actually very challenging to prove what this is. We're going to do it right now, and so you're going to see exactly how difficult it is. But I just want to make sure that we prove this rigorously and directly. So let's get into dealing with this limit right here and seeing what it evaluates to so we can get an exact answer for the derivative of this function. So in order to start negotiating this limit, all I'm going to do is add 1 and subtract 1. And so I'm going to say, and let's deal with this down here. Let's say that this green thing is going to be equal. I'm just going to write in green so that we know we're just dealing with this limit here. This is going to be equal to the limit as h approaches 0 of 1 plus e to the power of h minus 1 divided by h minus 1. Here I'm just adding 1 here on the left side and subtracting 1 on the right side. And adding 1 and subtracting 1 is not going to change the value here. Now I'm going to make 2 changes. The first change is I'm going to pull this first one, the positive one, outside of the limit because it's just a constant. It's not dependent on the variable h at all. It's not going to be affected by taking the limit as h approaches 0. The second change I'm going to make is I'm going to recognize that if I wanted to bring this negative 1 into this fraction here, I would just have to multiply by h over h, find a common factor, and I can actually put this into the fraction. And so I'm going to say that this is equal to 1 plus the limit as h approaches 0 of e to the power of h minus 1 divided by h. And now what I'm going to do is I'm going to sort of move in a little bit, and we're just going to be dealing with this expression here. We're not going to be dealing with all this out here, just what I have outlined here in red. And in order to make that more clear, I'm just going to write the next steps of this in red. So what we're going to do, so we're going to use our definition for e to the power of something that we derived earlier in the video with our compound interest formula. And so I'm going to say that this, what we have in red here, is going to be equal to 1, or it's going to be equal to the limit as n approaches infinity of 1 plus h over n to the power of n. I have to be very careful here to make my h's look different from the n's because I know that my handwriting is terrible. This is just going to be equal to e to the power of h. And then we're subtracting at h, and we're subtracting 1, we're dividing this whole expression by h. And so in order to move forward from this point, we're going to have to defer to our friend the binomial theorem. And this comes up a lot in mathematics, particularly in the fields of probability and statistics, but this just lets us deal with situations where we have binomial expressions being raised to some power in. You can imagine for very small numbers of n, this is going to be pretty easy to evaluate. For example, a plus b to the power of n, or to the power of 2, is just going to be a squared plus 2ab plus b squared. But you could imagine that as n grows larger and larger, it becomes more complicated to distribute out that entire multiplication and get a final answer. So there's a formula to deal with this situation, which is the summation k is equal to 0 all the way up to n of n choose k multiplied by a to the power of n minus k plus b, or times b to the power of k. And this n choose k here might throw some people off. N choose k is equal to the n factorial divided by k factorial times n minus k factorial. But if that doesn't make any sense and it seems a little eclectic, n choose k just represents the amount of ways you can pull k items out of a set of n items. That's the number of different ways you could pull out k things out of a set of n things. And so we actually don't even need this formula in order to do what we need to do in this one. So you actually don't need to worry about what this n choose k variable is mathematically. We just need to know it's the number of different ways you can pull out k items out of a set of n items. And so going back to our formula here, I alluded to it just now, but what we're going to do is we're going to use the binomial theorem in order to write a different expression for this right here. And so plugging that into our binomial theorem, we're going to forward here, we're going to get that this is equal to the limit as n approaches infinity. And then using our binomial theorem, a is going to become 1 and b is going to become h over n. So this is going to be equal to the sum, k is equal to 0 all the way up to n of, let's see here, we would have n choose k, and then we would be multiplying by a, which in this case is 1 to the power of n minus k. A to the power of n minus k, or 1 to the power of anything, n minus k, it doesn't matter what it is always going to be equal to 1. And so multiplying by 1, we're not going to change this expression. We can really just leave that out. Now we're dealing with this b to the power of k. B in this case is going to be h over n to the power of k. And then we're going to keep everything else the same. We have an h, we have a 1, and we're dividing by an h out front here. And what I want to consider is what are the first two values of this series? What's going to happen when k is equal to 1 and when k is equal to 0? Well, and I might do this in a different color here. When k is equal to 0, we have n choose 0. Well, how many different ways can you pick 0 items out of a set of n items? Well, there's only one way to do that, and it's to pick none of them. So n choose k here is going to be equal to 1, and then h divided by n to the power of 0, that's just going to be equal to 1. And so the first term of the series is going to be equal to 1. What about when k is equal to 1? Well, we have n choose 1 here. How many different ways can you pick one item out of a set of n items? Well, there's n different ways. So we're going to have n being multiplied by h over n to the power of 1 by h over n to the power of 1. That's just h over n. And so these n's are going to cancel, and this is going to equal h. So the first two terms of this infinite series are equal to h and 1. And here we are subtracting them. So one different way that we could write this is we could say that this is equal to the limit as n approaches infinity. And instead of adding those terms here and then getting rid of them here, so to speak, what we could do is we could just say that this is equal to us starting the series 2 steps later. So we're starting from k is equal to 2 instead of k is equal to 0. Once again, right here, we are just subtracting these first two terms where k is equal to 0 and k is equal to 1. So if we want to get rid of these, we could simply start the series from k is equal to 2 going up to n, where n choose k multiplied by h over n to the power of k divided by h. And now we've simplified this expression a lot, but we can simplify it a little bit further. The first thing that we could do is we could factor out this h outside of the limit, because we're taking the limit as n approaches infinity, and this h has nothing to do with that n. And so we can pull this out here, say that this is equal to 1 over h multiplied by the limit as n approaches infinity. And this, we're dealing with the sum from k is equal to 2, not 0, to the power, or 2n of n choose k multiplied by h. And I'm actually going to write this differently as well. I'm going to write this as 1 over n to the power of k multiplied by h to the power of k. And the reason I want to write this differently is because now this allows us to deal with this h term once again. So if we're starting from k is equal to 2 and going up to positive infinity, every single one of these terms is going to have an h in it. It's going to start with an h squared here, and it's going to go up from there from h cubed, h to the fourth, all the way up to h to the power of n, and we're doing the limit as n approaches infinity. And so if I have a 1 over h here, that's the same as dividing every single one of those terms by h, effectively reducing this power by 1. And so I can actually get rid of this 1 over h here. But I could go a step further, and I could multiply each one of these terms by h, and I could just drop this power one more. I could drop this power and say that this is equal to h being multiplied by the limit as n approaches infinity of the sum from k is equal to 2 all the way to n of n choose k multiplied by 1 over n to the power of k multiplied by h to the power of k minus 2. And the reason that I want this h out front is because this is just the product of two things, and if we go all the way back to our original equation here to what we have in red, we're taking the limit of this expression as h approaches 0. And so now we can just use direct substitution. If we take the limit of this expression as h approaches 0, we have this h out front, and so this entire thing is going to reduce to 0. It's actually not necessary to pull this h out because, like I said, every single one of these terms is going to have an h in it. That's pretty obvious. And so when you take the limit as h approaches 0, every single term is going to have a 0 in it, and so each one of them will go to 0, and the entire sum will go to 0. But I think it's a little bit cleaner to factor out this h just to show that this whole thing is going to go to 0. And so if you want, I would encourage you to pause the video here, just make sure that you followed along every one of these steps. But moving forward, this whole limit reduces to 0, and we're left with the fact that this limit here is, this one right here, is going to be equal to 1. And so if we go all the way back here to our step where we were trying to take the derivative of e to the power of x, what we have is that the derivative is going to equal e to the power of x being multiplied by the limit as h approaches 0 of e to the power of h minus 1 divided by h, and we have just proven that this limit is going to reduce to 1. And so the derivative of e to the power of x, the derivative of e to the power of x is equal to e to the power of x. In the next video, we're going to talk about something called implicit differentiation, which allows us to deal with functions that are implicitly defined in terms of some variable. Don't worry about that too much for now, but my point is that in that video, we're going to talk a little bit more in depth about logarithms and what they actually mean. So if you don't already know, logarithms are the inverse of exponential functions, and the natural log is the inverse of the exponential function with a base of the natural number e. And the natural log is going to be noted as ln. That's what separates it from other logarithms, which are typically written, for example, log is just log base 10, but if you wanted log base 2 of some variable, you would denote it like this. The natural log, instead of writing log base e, you just write log ln. But they're going to have these properties. It's the inverse of e to the power of x. So if y is equal to e to the power of x, if I take the natural log of both sides, so to speak, the natural log of e to the power of x is going to undo this exponential and leave us with x, and we have the natural log of y. Another way to think of this is that the natural log of some number is going to represent the power that we would have to raise e to in order to equal that number, and I hope that is clear from these two equations here. And so with this information in mind, this is going to allow us to negotiate situations where we're trying to take the derivative of exponential functions with general basis. So if we have the function y is equal to a to the power of x, and we want to take the derivative of this, we can say that this is equal to e to the power of natural log of a, because that's just going to equal a, e to the power of natural log a. Natural log of a is just the inverse of the exponential function, so when you take e to the power of that, it's going to be equal to a. It's going to be equal to this being raised to the power of x. And our exponential properties allow us to take down this x and just bring it into this exponent as the product of these two things. And so this is going to be equal to the e to the power of the natural log of a multiplied by x. Now we can take the derivative of this using the chain rule, because here we have this outside function e to the power of x that we know how to deal with. And so we say that the derivative here, dy dx, is going to be equal to the derivative of the outside applied to the function at this point. So e to the power of natural log of a being multiplied by x, multiplied by the derivative of the inside function here, natural log of a times x. Don't be thrown off by this natural log of a. This is just going to be some constant. And so when you take the derivative of a constant multiplied by x, it's just going to be equal to the the value of that constant, so natural log of a. And this is equal to, just working backwards like we did in the beginning, e to the power of natural log of a to the power of x multiplied by the natural log of a. And all of that is to say that the derivative of a to the power of x, the derivative of a to the power of x with respect to x is going to equal a to the power of x being multiplied by the natural log of a. So this allows us to deal with situations where we have general bases for exponential functions as well. Now that we've proven what the derivative of e to the power of x is, it allows us to deal with all of these situations. So in order to conclude this video, I want to talk about an alternate way that you could approach this problem. And this is just going to be from a pure mathematician's perspective. There's going to be no mentions of compound interest or anything like that. This is just going to be within the realm of calculus. So I actually prefer this method, but it goes against what most people have as their intuition to the understanding of the natural number e. And so this just ignores all of that. It just starts from the ground up and establishes what is a function whose derivative is equal to itself. So in order to do this, we're just going to ask ourselves, we're going to assume that there is some function wherein f prime of x is going to equal f of x. This is our foundational principle here. And the other assumption that we want to make is because as mathematicians, we know that by nature, this function is going to be exponential. This is what exponential functions are. They are functions that grow in proportion to the size of those functions. And so we know that this is going to be an exponential function. We know that this is going to take the form of some constant being multiplied to the power of x, some constant to the power of x. And so we know that the derivative of this function is going to equal the function itself, and it's going to take the form of some exponential function. And I think with this in mind, we actually have enough information to figure out what this function might look like, where the derivative of itself is equal to itself. And so if we know that this is going to take the exponential form, then we know that the value of this function at x is equal to 0, c to the power of 0 is going to equal 1. And if we know that the derivative of the function is equal to the function, then f prime of 0 is also going to be equal to 1. Okay? And so if we know that f of x at 0 is equal to 1, and we know that f prime of x at 0 is also equal to 1, then we can start to notice a few things, which is the first is that the derivative of 1 is not equal to 1. And so if we want this to equal the derivative, then we have to add some term here whose derivative is equal to 1. And that would be x. X is the function whose derivative is equal to 1. And so now when we take the derivative of this top function, we have the derivative of 1, that's just 0, so that's good, plus the derivative of x, which is equal to 1. Now these two things are equal, but wait a second. Now the derivative here is not equal to the function, and so we have to add the x here. But once again, we run into this problem where we don't have a derivative of x, and if we want to get a derivative of x, we need to add some term here. What function has a derivative of x? Well, x squared has a derivative of 2x, so we would have to do 1/2 times x squared. If we took the derivative here, these 2's would cancel, that 2 would come out as a coefficient, and we would be left with x. Okay, now we're good. But wait, here in the derivative, now it's not equal, and so we have to add that term there as well. And you might be able to imagine that this is going to continue on forever, but let's see what the next term would be. So if we want the derivative of this function to be equal to this expression here, then we know that we would have to have x to the power of 3, because that's going to give us x squared as a derivative. It's going to give us 3x squared to be specific, but there would have to be, let's see, what would we have to put out front in order to get 1/2 if we have a 3 out front? Well, we would have to divide by 6. And so up here, we're going to have 1/6, or maybe a better way to write this is 1/2, because that's what we want, being multiplied by 1/3, because that 3 is what we would have when we take the derivative of x cubed. And now we would have to add this into our derivative expression here, and we would just have to keep doing this forever. And our next term here would be 1 over, I'm not going to spoil it, but if you do the math, this will be 1/2 times 3 times 4 multiplied by x to the power of 4, and you would have to add that term here. And so what we seem to be getting here is that this is going to equal an infinite series of x to the power of n being divided by, well, what's this? This is just n factorial, which is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And so this is going to give us our value for c to the power of x. This is that function whose derivative is equal to itself. This is an alternate way of expressing it in terms of an infinite series. And what I want to point out is that if this is equal to f of x, that's one way of saying that this is equal to c to the power of x, and if we want to find out what c is, what the base of this exponential function is, whose derivative is going to be equal to itself, all we have to do is take this series evaluated at x is equal to 1, because that would give us c to the power of 1, which would be equal to c. And so if we do that down here, we could say that c is equal to, and we just plug in 1 anywhere that we would have an x. So we would get 1 plus 1, we plug in a 1 there, plus 1/2 times 1 squared, well that's just 1. And in fact, anywhere where we have these x to the power of anything, 1 to the power of anything is just going to be equal to 1. So we're really just adding together these coefficients. So we have 1 plus 1 plus 1/2 plus 1 over 6, that's 2 times 3. And we're multiplying by 4 here, so we get 1 over 24. Multiplying by 5 here, so we would get 120, I think. And then we multiply by 6, that would be 1 over 720. And then it gets a little bit harder to do in my head, so I'll just do 720 times 7, and then I'll add one more. I'll do like 720 times 7 times 8. And each one of these successive terms is going to get smaller and smaller and smaller, but I think if you were to plug this into your calculator, you would find that this is going to be approximately equal to our 2.718 blah blah blah. And so this is actually equal to e. So this is one way of deriving this function without having any prior knowledge. This is just the way that purely from a calculus perspective, how we can figure out what this function is when we take the derivative and it is equal to itself. And you can imagine that if you took this function right here and you took the derivative, what would happen? This is an infinite series. This would be 0, then this would become 1, and then this would become x, and then this would become 1/2 x squared, and it would go all the way down the line, and yes, indeed, it would be equal to itself. And so this is just an alternate way of deriving that function from a purely mathematical perspective. And the last point I want to make before I conclude this video is that we have this expression for e here, and I'm just going to replace our c, which was our arbitrary base for an exponential function whose derivative was exactly equal to itself. We know now that the base of that exponential function is going to equal the transcendental constant e, and we have this expression to define it where we have 1 over n factorial, the series sum of that, as n approaches infinity. And so we have this way of expressing e, where e is equal to the sum, or the limit, as n approaches infinity of the sum from k is equal to 0 to n of 1 over n factorial. And if you plug in numbers here, you'll find that for 0, this is 1 over 0 factorial, that's just equal to 1. For 1, this is 1 over 1 factorial, which is just equal to 1. And then you get 1/2, and then you get 1/6, and then you get 1/24, and it's all the same numbers that we derived. And what I want to point out is that if you do the math, which we're going to do, we can find that our original function for e, or our original expression for e, which was represented by the limit as n approaches infinity of 1 plus 1 over n to the power of n, I want to show that this is going to be equal to this expression up here. And so in order to do that, we're just going to defer to our binomial translation of this. So this is going to equal the limit as n approaches infinity. Once again, just borrowing from that binomial theorem. This is going to equal the limit as n approaches infinity of the sum, k is equal to 0, all the way up to n of n, choose k. And we're going to do we're going to do 1 to the power of n minus k. That's always going to be equal to 1, so it's not going to change the value of any of these terms, so we can just leave it out. Multiplied by 1 over n to the power of k. And what is this going to give us? Well, what's our first term here? We're going to have k is equal to 0, n choose 0 is just equal to 1, and then we have 1 over n to the power of 0, that's just equal to 1. So our first term is going to be equal to 1. It's our second term. We have k is equal to 1, that's going to be equal to n being multiplied by 1 over n to the power of 1. So this is just going to evaluate to n times 1 over n, which is just equal to 1. So we can write that in here. And now you might be thinking that this is going to get a little bit complicated because we're taking the limit as n approaches infinity, and we have this in choose k variable here, and as we move past the point where k is equal to 1, now we need to do some mathematics here on this in choose k variable, and when we have the limit as n approaches infinity, you might think that it's impossible to deal with, but watch what happens. So we're going to have n choose 2 here being multiplied by 1 over n to the power of 2. This is going to be our third term here. n choose 2 is going to equal n factorial over 2 factorial times n minus 2 factorial. And n factorial is going to be equal to n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. And n minus 2 factorial is just this section here. And so when we're dividing these terms, all of this is going to cancel, and we're just going to be left with n times n minus 1. And so we have that this is going to reduce to n times n minus 1, which is just going to look like this, being divided by 2 factorial. So that's n choose k. And then we're multiplying by 1 over n squared, which is just going to be 1 over n squared. And now what I'm noticing is that this n is going to cancel with one of these, and we'll be left with n minus 1 over 2 factorial, which is just 2, divided by n. And so I think we could actually break this up and say that this is equal to n over 2 minus 1 over 2, all of this being multiplied by 1 over n. And so now we have that this is going to cancel out with the n in the first term, and we'll get 1/2 minus 1 over n. But remember, with this series, we're taking the limit as n approaches infinity of 1 over 2 minus 1 over n. And as this n tends towards infinity, this is going to tend towards 0, 1 over n. And so we're left with just 1 over 2. And so if you apply all of this and put this into our expression, we're going to get that our third term here is equal to 1 over 2. And if you keep doing this, you do all the math on each one of these terms, you'll find that you're going to see perfect agreement with what we determined was our expression for E simply from calculus. And so these are indeed equal. Thank you all for watching, and I'll see you in the next video with implicit differentiation, and we're going to cover logarithms as well.